Okay, ladies and gentlemen, we're back. This is number 6, example 7.6. We left off our video. I said I was going to do this example next about the moment reaction diagrams for this situation. A is a thrust bearing, which means you can have an AX. You can have an axial component of the force. C is a journal bearing, which means the shaft can slide in the axial direction. There's no opposing force. So, but anyway, since all the forces are vertical, you don't have any CX. Therefore, you're not going to have any AX. You're not going to have any tensile forces. They're all going to be vertical. So we calculate the reaction forces. Well, you guys have gone through problems like this before. So AX is going to be 2.5 newtons, and CX is going to be CY. Excuse me. AY is going to be 2.5 kilonewtons pointing up. CY is going to be 2.5 kilonewtons pointing up. Here's a free body diagram. That means V, there's V right there, for the left-hand portion. It's going to have to be 2.5. The moment around this point is going to be m plus negative 2.5 kilonewtons x. 2.5 kilonewtons x. M plus a negative, which we solve the equation, m equals 2.5x kilonewton meters. Okay, now we look at the right-hand portion of the diagram. So we have two forces now. We have this 5 kilonewtons plus the reaction force at A. And then everything else looks the same. You have total x, x minus 2. Draw very good diagrams, ladies and gentlemen, when you're doing this kind of thing. That means V has to be, in this case, V has to be a negative 2.5 kilonewtons. The moment then is m positive counterclockwise minus 2.5 kilonewtons times x, that's the moment due to this, due to force A, plus 5 kilonewtons times x minus 2. There it is, 5 kilonewtons, x minus 2, 2.5 kilonewtons times x. This is a times x right here. And then moment plus all this stuff. Solving for moment, then, we get this expression. And now we can draw the diagrams. So we learned that the shear force is 2.5 kilonewtons. When it comes to this point, it drops to negative 2.5. Now, at this point, we have a force acting up and a force acting down. It should return to 0. This plus this should equal 0 at the ends. That it starts at 0 over here. Then this force here pushes it up to 2.5, and this force here pulls it down to negative 2.5. The moment equation is linear. Now let's go back to the first one. There it is. 2.5x kilonewton meters. So it's just a linear slope, just straight up. There it is, linear slope straight up. And then on the way down, 10 minus 2.5 kilonewton meters, 2.5x. Let me repeat that. M equals 10 minus 2.5x with the units kilonewton meters. At x equals 2, then that means it's 5 kilonewton meters. And from the previous equation, at x equals 2 meters, it would also be 5 kilonewton meters. So the two curves match up in the middle. It's just one is going down, this one's going down, this one's going up, maximum 2.5. And this is what you want to know. These are the kinds of things you want to know. That can the beam withstand this? Can the beam withstand either the minimum or the maximum shear stress? Okay. Now I did this in Excel also, and here's the Excel spreadsheet. Just to program in, here's the equations. So moment equals 2.5 x going up. And I did this kind of thing where I go from 0 to a very small number so that we get a vertical line straight up. It appears to be a vertical line straight up. If I didn't do that, I'd have a little bit of an angle. And that doesn't look so great on the graphs because we know there's not angle. We know it steps up and then it goes and then it steps down, then it goes, then it steps back up again. And this is to make the appearance, these little numbers here are to make the appearance look like it's going straight up and down. Same thing at the very end. Okay, M is 2.5x. Here's A2, column A, row 2. Here's these are the formulas, by the way. I'm showing the formulas for you guys. Constant, and then when it gets halfway, it goes to negative 2.5 kilonewtons for the shear force, and moment is 10 minus 2.5 times x. Okay. So this is how to program the graphs in Excel. Just wanted to show you guys that. Next example. So now we have a pure distributed force. The previous example had a point force, a point load. So I work through, we have a roller on one side, a pin on this side, and so we can have AX can be non-zero, but it's not because there's no other horizontal forces. AX plus nothing equals nothing. So AX has to be 0. The sum of the two, 6 times 9 divided by 2, or 27 kilonewtons. That's the area under this triangle. That's the total force. So AY plus BY has to sum to 27. And we can separate it out by the moments. That 27 kilonewton force is acting at 6 meters from A. So we can find the moment around A. It's clockwise, so it's negative. And that's equal to 9 times B, which is counterclockwise. And we get this result. BY has to equal 18 kilonewtons, AY has to equal 9. Now, we're just looking at the free body diagram of the portion where we cut it at point at X. We go X distance and cut the beam, and we draw a free body diagram. No horizontal forces, vertical and moment here. Then we ask, what is the equivalent force here? So we've got to keep the triangle first. We can't just use the 27 kilonewtons acting at 6 meters. We got to go back to the triangle. We got to go back to a distributed load and cut the beam, and then we find the equivalent force right here. 1/3 x squared kilonewtons at x over 3 from the right side. So the sum of these three, you got to solve the equations. There we go. The shear force is going to equal 9 minus x squared over 3. Let's see if that makes sense. Oops. There's the x squared over 3 right here. The shear force is 9 minus this minus V is going to equal 0. So V equals a 9 minus 1/3 x squared, which is, of course, what we have right here. And you can find the 0. It's at 5.2 meters. Just solve this equation, set the shear force to equal 0. When will it go? It starts out positive 9 kilonewtons. Then it goes down and it crosses. And at the very end, it's going to go back to 0. Okay. Later on, we're going to see, well, in just a second, we're going to see this is where the maximum moment also occurs. So we get a maximum moment at this 5.2 meter value. Let's take a look at the moment equation, though. So total force here, x times 2/3 x, so that's x squared over 3, 1/2 x times 2/3 x. That's the area under the triangle, which gives us 1/3 x squared. The moment plus 1/3 x squared times x over 3, so that's at x cubed over 9, minus 9x. That would be your moment. 9 times x, there it is, minus x cubed over 9. And they didn't actually derive the equations for the moments. So I just talked you through it. Replace 5.2 with x and you get the equation for the moments. And here they do it now. They didn't do it before. Slides are slightly out of order. Here's the diagrams plotting 9 minus x squared. This is the 5.2 meters we found. This is it's not a parabola. It's pretty close to a parabola. You can factor x out. X times 9 minus x squared over 9. And we get a maximum. Okay, that's a repetition. Now, I'm going to stop the video here. We're going to consider this next. Lots of mathy stuff, as you can see.